Hello, I'm today in presence of Markus Mosbech, who recently published pre-published an article on the archive called "The Full Boltzmann Hierarchy for Dark Matter Massive Neutrino Interactions." So Markus, you are here today with us to discuss it. So perhaps you want to present yourself first?
Yes, I'm Markus Mosbech. I am a PhD student here at the University of Sydney, and I work mostly in dark matter.
All right, so you are talking to us about dark matter. Perhaps you would like to give us a broad overview of what dark matter is?
So when we look into space, it turns out that about 80% of the matter in the universe is invisible to us. And thus we call it dark in the sense that it does not emit or generally interact with light. And there's a variety of observations confirming its existence, but it's still a great mystery what it actually is. So there's a lot of effort that goes into looking into various models and doing various tests to see, is there any way we could get some more information about this?
All right, and so the title of your article also mentions neutrinos, so what about them?
The neutrinos are another slightly less mysterious component, maybe. It still has some weird properties. The thing is that neutrinos are very light, very weakly interacting particles. As far as we know, they only interact through something called the weak force. And the thing about neutrinos is that they are very light, but apparently not quite massless. There are three different mass states that do not quite match the three different so-called flavor states. And that means the flavor states will oscillate, which gives us proof that the neutrinos have mass. And
so what do you know? What do we know about their mass?
Well, from the neutrino oscillation experiments, we can get the squared mass difference between the three mass states. So we can sort of calculate from this what is the minimum mass of the sum of all three neutrinos. At the same time, there are different experiments such as Catrin that measures from different reactions the maximum allowed energy, maximum allowed mass of neutrinos, while we also look at what is the cosmological effect of having neutrinos that have mass. And both can set some pretty stringent upper bounds on neutrino mass, particularly cosmology, where Catrin puts the upper limit of a single neutrino at around 1 electron volt. The cosmology puts the total upper limit of the sum of the neutrino masses at a bit over 0.1 electron volt. So assuming our cosmology is correct, this is the most stringent bound on the neutrino mass we have.
All right. So in your paper, you consider combining dark matter and neutrinos. So why should we consider this combination?
Well,
one
thing is that it's good to consider all sorts of things when we really have not much of an idea what's going on. And in particular, because neutrinos and dark matter are both fairly mysterious in some ways, it's possible that they could have some interaction. And what I'm doing here is something that, in essence, no one has ever done before, because in previous studies, we have either introduced massive neutrinos into our cosmological simulations, or we might have, because they're so light, it's often used as an approximation to treat the neutrinos as massless. And in these simulations, there have been implementations of neutrino interacting with dark matter. But the new thing I've done is that I've implemented this interaction for the case where the neutrinos have mass.
All right, so you talk about interactions. Can you give us an idea of the rate of interaction of these particles?
Well, it would have to be fairly low, really. That's one of my key results, is that I've implemented this framework in code so that I can calculate what is the effect of such an interaction on the universe at large scales. So doing this and comparing the data allows us to set upper limits for how strong the interaction can be. And while this depends, of course, also on the mass of our dark matter particle, we get something that is several orders of magnitude weaker than a normal electromagnetic interaction for a fairly standard heavy dark matter.
All right. Well, that seems logical because dark matter and neutrinos are fairly weakly interacting particles. Although, of course, this is a specific interaction you are considering.
Yeah, we've implemented a fairly generic interaction where we just put in a constant cross-section similar to Thomson scattering between electrons and photons. The process we have implemented is really very similar to that.
All right. Okay. So in the title of your article, you also mentioned Boltzmann hierarchy. So I suppose this is referring to the Boltzmann equation, which describes the universe as a fluid, right? Can you?
Yeah. So the Boltzmann equation describes the evolution of the distribution function of a given species, and when we compute this, we often take a Boltzmann hierarchy rather than solving the pure Boltzmann equation, in that we can do a Legendre decomposition and integrate over momentum space to reduce the number of things we have to care about, so to speak. So, for instance, dark matter can be modeled by only two equations, one for the evolution of the density and one for the evolution of the velocity field. But problem is with massive neutrinos that since they have mass, but it's very small, they are very energetic for a large part of the evolution of the universe before they are redshifted to lower energies. And this means we have to be more careful in treating them. And thus we cannot perform this integral over momentum analytically, but we have to do it numerically and solve the Boltzmann equations individually for different momentum bins. And this also means that I had to recalculate the Boltzmann hierarchy in the presence of this interaction to see what would this look like.
All right, so I suppose that's where the Boltzmann code comes from. Which sort of code in particular have you been using?
Well, this is it's a fairly standard thing in computational cosmology to use a Boltzmann code. Right now, there are two state-of-the-art Boltzmann codes on the market. There's CAMP and CLASS. Personally, I've used CLASS, haven't really looked into CAMP. But they are very similar in what they do. And CLASS, what it more or less does is that it solves the whole universe to linear order. That's the thing about the Boltzmann equation, that if you go to Fourier space, you can solve it as a very simple set of coupled differential equations. And this is much, much cheaper computationally than, for instance, running an n-body code. So what I can do is I can calculate the whole evolution of the universe in a matter of seconds on my normal laptop. But being at linear order, it lacks a lot of the effects at later times, specifically nonlinear clustering of dark matter and so on and so forth. So the thing is that one of the main observables we have in cosmology is the cosmic microwave background. And the cosmic microwave background was emitted when the universe was only around 370,000 years old. So around a redshift of SED 1100, I think, maybe 7,000, something like that. And these photons then have imprinted the structure at that time while the universe was still very well described by this linear theory. And because photons are massless, they do not have these nonlinear clustering effects to a very large degree. So our linear simulations match very well with the observed CMB, and thus we can do some really cheap predictions, or one of the best data sets that we have.
All right. Well, so you are probing the first, like the neutrino to dark matter interactions in the first light of the universe, right?
Yeah, I'm really probing it all the way through, but of course my data for later times might have to be taken with a grain of salt. What is interesting is that adding the neutrino mass to the calculations means that the interaction rate is suppressed by a factor of momentum over energy squared, so that if the neutrino was massless, the whole energy would be in its momentum, so this would always be 1. But the momentum over energy squared means that the interaction will quickly be suppressed once the neutrinos lose energy and become more relativistic. And this means that, in fact, our neutrino interaction decouples long before the CMB is emitted, and thus there isn't really that much of a late time effect of this effect. It is an early time effect.
All right. Okay. So are there particular regimes? You told us about linear for the CMB, but what about dark matter? Are there specific candidates or the specific regimes of cross-section and the different parameters of dark matter you can or can't probe?
No, well, what I have done is that my derivation of this interaction term is done in the regime of a fairly heavy, fairly cold dark matter species. So they're pretty much normal CDM generic plus this interaction. So I haven't, like, it would have to be redone entirely if we had some sort of cold light dark matter candidate like an axion. So it's given, like, I'm using a fairly generic prescription. So unless you're using something exotic, then this works.
All right. And so now what we're all interested in is to know the results of your work. So what does the dark matter neutrino interaction change?
Well, the dark matter neutrino interaction has some effects on the CMB in that it allows the dark matter to more easily interact, have a larger effect on the CMB at early times, which yields a small increase in the TT spectrum and a slight shift of the peaks. But the main effect is really found in the matter power spectrum rather than in CMB. And the matter power spectrum is sort of a measure of how much structure is in the universe. And this matter power spectrum will be strongly suppressed at smaller scales due to this interaction because of something called collisional damping, in that normally the neutrinos will just free stream away from the overdensities, but now it will sort of collide with the dark matter particles and generally wash out structure. And this would generally lead to like a slight delay in the nonlinear structure formation, because the general overdensities of dark matter will be smaller at the time compared to the non-interacting case.
All right. I also saw something about H0 and sigma 8 tension in that paper, so perhaps you want to write on that.
So there are, among other problems in cosmology, two fairly large and easily identifiable. The primary one is maybe the H0 tension, which is that H0, the expansion rate of the universe today, can be measured both by probing early universe phenomena and late universe phenomena. And there is quite a discrepancy between the value is measured. And the question is if someone's doing their job wrong or there is some new physics going on. I may be a bit harsh saying they're doing the job wrong, but they might have some uncertainties they haven't accounted for, or some systematics that they are unaware of. And but the issue that would allow, the thing that would allow everyone to save face is that if we had some new physics that might change things up. So this was one of the original motivations for doing this work, is that maybe this could help reconcile the values of H naught. It turns out it does not, having this interaction on, it has no noticeable effects on H naught. The other tension you mentioned, the sigma 8 tension, is the sigma 8 is sort of a statistical parameter describing the amount of structure in the universe at a given scale. And again, there are different experiments that measure different values of it, and either they are missing something or there is new physics going on. And what we find is actually that including this interaction helps bring the data from the Planck satellite in much greater agreement with other data sets, such as the KIDS data set, in what the value of sigma 8 should be. So that's a nice result, I think.
So you shift that value like towards the middle between those.
No, so it allows a much greater parameter space for the Planck data, in that it's sort of, while if you look at the normal Planck data release, it's this nicely normally shaped normal distribution, but when I turn on this interaction, we get this sort of skewed distribution that has a much larger allowed area at lower values of sigma 8, which is ideal for matching it with these other data sets that are in tension.
All right. So what you mean is that it's some sort of interpretation, to say, of the data?
Well, the thing is, like, a larger sigma 8 means more structure. And what my interaction allows is to wash out some structure without really changing the CMB data much. So we can still be in good agreement with the normal predictions for CMB that are very well in agreement with what's measured by Planck, but we can change the matter power spectrum. We can suppress power at small scales and thus lower our sigma 8.
All right, okay. All right, so what sort of outcomes do you expect in the future from that code and that work?
Well, the thing that's nice is that because well, one thing we can do is we can use the output of the code to start some n-body simulations, because that will really help us to see what is the real effect on the late time nonlinear universe.
All right. Okay, so I think we are going to wrap up the discussion here, unless you have something more you want to add.
No, I think that's it. Thank you very much.
All right, thank you, Markus. See you next time.